Right, so now we're going to talk a bit about quadratic inequalities in two variables. And just like linear inequalities in two variables, showing a solution to a statement given in this form is going to require a graph. And so we're going to dive right in with a few examples of what solutions to quadratic inequalities in two variables look like. This is example 1 off of page 490. And what we're asked two parts. We're asked to graph the inequality y less than negative 2 times x minus 3 squared plus 1. So this is almost identical to just graphing a regular quadratic. If I wanted to graph the quadratic y equals negative 2 x minus 3 squared plus 1, important pieces of information would be it has a vertex at 3 and 1. It opens downward. And it has a stretch of 2, which we'll use in a second. So the point 3 and 1 is here. Opens downward. If I work this through, it would have a y-intercept at negative 16, negative 17, which I'm pretty sure I don't have on this graph. So I won't run across, words. So I won't quite run across the y-intercept in the amount of graph that I've shown here. But that vertical stretch of 2 means instead of going over 1 and down 1, I'd go over 1 and down 2. Instead of going over 2 and down 4, I'd go over 2 and down 8. And symmetry would have the same thing happen on the other side of the vertex. And that's enough for me to plot out a quadratic form. Now, instead of just drawing a straight line, a solid line, like I would with the equality, since this is an inequality, the fact that it's less than means my shape will be outlined with a dashed line or dotted line. And then I need to think about how I deal with the inequality part of this. So, if I need my y values to be less than these x values, everywhere along the dashed line my y values are equal to those x values. So if I need my y values to be less than that, that's going to be the area underneath the line. Notice that I'm not saying inside the line or outside the line, I'm saying under it or above it, because that's important, and we'll see that in another example or two in a second. But for now, there's our inequality. Take up that space there. The dashed line is the line of the quadratic. It's dashed because my y is not supposed to be equal to those numbers, and it's underneath the line because y has to be less than those values of x. A B part of that example asks us to check if 2, negative 4 is part of the solution. Solution area. So, I can look on my graph, and it sure looks like it will be. But as to how you can check fully, y and negative 2x minus 3 squared plus 1, y is simply negative 4, x is going to be negative 2 times 2 minus 3 squared plus 1. 2 minus 3 is negative 1. Squared is positive 1. 1 times negative 2 is negative 2, plus 1 is negative 1. And in this case, negative 4 is less than negative 1, so this is part of the solution. Okay. I'm going to modify example 2 a little bit. It is coming from example 2 in your textbook, but I'm going to change it up just slightly to say that I want a graph where y is less than or equal to x squared minus 4x minus 5. Your book example is greater than or equal to, and it's worth taking a quick look at, but there's something that comes up in the less than or equal to in this case that I want to show. Okay, so again, I'm going to talk about graphing the associated equation that you could think about. And this is not in vertex form, so it's a little bit more work to pull out the vertex, but it is worth noting it does factor quite nicely to x minus 5 times x plus 1. So this has x-intercepts at x equals negative 1 and 5. Therefore, its vertex has to be at an x value halfway between those at 2. And that would give me a y value of 2 squared, which is 4, minus 8 is negative 4, minus 5 is negative 9. So I know where my vertex is, I know where my x-intercepts are. That's enough for me to draw a graph. So 1, 1, negative 1. I'm interested in the vertex at 2 and negative 9. 6, 9. And my zeros at negative 1 and positive 5. That's enough for me to draw a curve of this. Since the equality is part of this, I will draw a solid line for my parabola. Worth noting my y-intercept should also be at negative 5, just for an extra point to help you out. So there's our parabola. Now as far as shading goes, I want my y values to be less than this expression of x. Since everywhere along this line, my y values are equal to that expression of x, I want y values less than the ones represented by this line. That's going to be this area under the curve again. But you'll notice that under the curve looks very different in this case than it did in the last example. Which is why I want to stress that I'm talking about terms of under and over and not inside and outside. In each of these two diagrams, I have shaded in the region underneath the curve. In this first example that was inside, and the second example that was outside, but in each case it was underneath. It was underneath the curve. And that's what's important to remember for these inequalities. Less than is going to mean under the line. Greater than is going to mean above the line. And sometimes that'll be a difference between inside and outside. Alright, one more example that I'm going to look at, and that's all I'm really going to talk about with this right now. And this is example 3 off of page 493. Which is everyone's favorite, the word problem. And you will probably want to look along at the example in the textbook for this because there's a diagram there which will be a little helpful. It talks about a parabolic reflector, which is sometimes used in microphones to be able to hear a lot of sound in a certain region of space. Parabolic microphone has a parabolic reflector attached that directs incoming sound to the microphone. Rene, a journalist, is using a parabolic microphone as he covers the Francophone Summer Festival of Vancouver. Describe the region that Rene can cover with his microphone if the reflector has a width of 50 centimeters and a maximum depth of 15 centimeters. And in your textbook they show this graph with the parabola sort of centered at the low point of where the reflector would be. It's not going to be nicely to scale, so I apologize for that. Not even going to be that nice parabola. I apologize for that as well. The important things for us to build into this are that the parabola is 50 centimeters wide at its maximum and 15 centimeters deep. That means these points are going to be at 25 and 15 and negative 25 and 15. And we are asked to describe the region of space where the microphone will pick up sound. And that's really going to be everything up here. That space is what we're interested in describing. So, we already know how to work out a quadratic with this. In vertex form, y would equal a times x minus h squared plus k. Our vertex is at 0, 0. So this is immediately just going to look like ax squared. And it has to pass through the point 25 and 15. So 15 is going to equal a times 25 squared, or a would equal 15 over 25 squared. If we simplify that a little bit, we'll go to some prime factors just to make life fun. 25 times 25. This will be 3 over 125. So the parabola is y equals 3 over 125x squared. However, I'm not interested in just the parabola. I want this shaded area up here. So that is the area above the parabola. So I'm interested in the greater than portion of this program. So the shaded area is y greater than or equal to 3 125ths fx squared. So the area covered by the microphone is the area where y is greater than or equal to 3 125ths x squared, and where x is between negative 25 and 25. There. So there's a few different examples of working with quadratic inequalities in two variables. Fairly straightforward realizations of the work with quadratics that we had done before. So I will leave it there for now, and there'll be some questions attached in the Google Classroom. All right. Thanks for your time, everybody.